Okay, so we have yet another snow day, so we get to do more of this. And I wanted to kind of continue what we've been doing, whereby we essentially said one of the goals here is to take everything you did in Calc 1 and Calc 2 and then just kind of expand on it from a single variable function to a multivariable function. And at this point, in Calc 1, you had derivatives, and now we have directional derivatives. We also have partial derivatives. And then one of the first problems that you do in Calc 1, once you define a derivative, you define the equation of the tangent line to a graph at a point. And as far as it goes, I think I kind of already wrote this out here. The way, it can be written in different ways, but essentially the equation of the tangent line is still the equation of a line. So say you can have point slope form of the line, and you can write it this way with x's and y's, or you can write it this way just in terms of using f of x and x. And then sometimes you write it this way in point slope form, sometimes you kind of rearrange it and it looks more like this, which is slope intercept form, if you algebraically manipulate it. But the point is, that's the equation of a line that you know from pre-calc, and then in calc you say, okay, well, all of this will stay the same, but now I know my slope is now my derivative, so that's f prime of x times x minus x sub 0 plus f of x sub 0. And again, there's different ways to write this. I think this is one of the standard ones. It's been a while since I taught Calc 1. But you have that, and you say, well, okay, it's just the equation of a line, just like it was in pre-calc. The only difference is now my slope can change because it's a derivative, but it's really the exact same thing. So then the question becomes, now that I have derivatives, directional derivatives and partial derivatives for multivariable functions, do I get the equation of a tangent line? And the problem is, and I'm not going to try to necessarily graph this, but if I have some surface like this in space, well then, if I pick a point on that surface, like right here, well, I could have a line going this way that's tangent, but I could have a line going that way and a line going this way. And it becomes apparent relatively quickly that I wouldn't necessarily have one tangent line there, so that doesn't really work. So then, instead of defining a tangent line, we do what we've done for a lot of other things. We just kind of expand by one dimension. And instead of having a line, we can define a tangent plane to the surface, where say, I think we've used the paraboloid a lot. So if I have like a paraboloid like here, something like that, then maybe if I have a point on that paraboloid like right here, instead of trying to draw a line, because again, I could draw a line this way, I could draw a line that way, I could draw it over here. I'm just going to define, and I know this won't look great on the whiteboard with multiple colors and all that, but I'm just going to define a tangent plane that will sit like this, only touching the graph at that one point. But similar to the idea with tangent lines in Calc 1, well, tangent lines are still just equations of lines, so I use my understanding of the line to kind of generate the equation of the tangent line. Well, that's a plane, we'll call it a tangent plane, but in principle, it's the exact same idea. This is just the equation of a plane. And I know to define a plane, I need a point on the plane, but just like with the tangent line, where I take the derivative at the point, here I can just use the point on the surface that I care about, and then I just need to find a normal vector to that plane. And as far as it goes here, in order to define the normal vector, there's different things we could try, but what we're going to do is essentially say, up to say this picture, I'm going to look at say f sub x, the partial derivative with respect to x, and the partial derivative up to my ability to draw them reasonably well, just to make this look good, with respect to y. And then I know this will be the derivative in the x direction, the derivative in the y direction, and I know that these will be orthogonal to each other. And then I know, well, if I want to get this normal vector to the plane, as long as these are on the plane, then their cross product will be normal. and then I'll have my normal vector to my plane. So I at least have a way to go here. First, though, I have to define vectors that go in this direction and that direction. And as far as it goes, you could kind of sketch out a really long example here to get those directional derivatives, those directional vectors. It's actually not that big of a deal, though, and I don't want to take time in this video to do that. So we're just going to say, we're going to define v sub 1, which will be the direction vector in the partial derivative with respect to x direction, and it's just 1, 0, f sub x at the point x sub 0, y sub 0. Which I would point out makes sense. It's the partial in the x direction. I don't worry about the y direction, and then this is just scaling it, if you will. And then I can do the exact same in the y direction. So now it's 0, 1, and then this will be the partial with respect to y. And again, in class, we may actually sketch that out. I just don't want to do it here in the video. But now I have those, and essentially now, this is my partial derivative. This will be v sub 1. This will be v sub 2. I know those will be orthogonal. To get my normal vector to the plane, I just take their cross product. So I do v sub 1 cross v sub 2. And all of you know how to take cross products. So again, to kind of save a little bit of time here, that would just be 1, 0, f sub x crossed with 0, 1, f sub y, which if I actually do that out, will be negative f sub x, negative f sub y, 1. And that will be my n, my normal vector to that tangent plane right there. But then once I have that, now the equation of my tangent plane will just be the equation of a plane. And I already know how to do that. Let's see. I think the equation we used was a x minus x sub 0 plus b y minus y sub 0 plus c z minus z sub 0 equals 0. And yeah, we're all perfectly on screen. Good. So now, just like I did with the tangent line, I can just kind of fill in here. A, B, C is just my n. So that's negative f sub x. And I will point out, and I've kind of pointed this out in class before, these are the partials at the point, but just for brevity's sake, I'm not writing f sub x sub 0, y sub 0, and all that, because I only have so much room on the board. So negative f sub x minus x sub 0, plus b is negative f sub y minus y sub 0, plus c, which is 1, z minus z sub 0 equals 0. Now, I'm just going to rearrange that a little bit and solve it for z. And I'll also point out, just like over there with the tangent line, I can write this as z sub 0, but if I kind of use function notation, that point z sub 0 is just f of x sub 0, y sub 0. So now if I rearrange this and solve it for z, I get that z is equal to f of x sub 0, y sub 0, plus f sub x times x minus x sub 0, plus f sub y times y minus y sub 0. And again, these are the partials at the point x sub 0, y sub 0. And I would point out, as we kind of pointed out in class, that's the equation of the tangent line. The only difference between the equation of a tangent line and a regular line is instead of having m, a constant slope, we get the derivative, which makes sense. Here now I'm talking about a tangent plane, and I get something that looks the exact same as that. The only difference is instead of having regular derivatives, now I have partial derivatives, and I have an extra variable because it's a multivariable function. And I've kind of mentioned this before. When I was a student, I tended to miss the forest for the trees a lot. And then you essentially end up having to memorize the equation of a line, the equation of a tangent line, the equation of a tangent plane, and all of this stuff. Or you can just kind of understand it, and this and that are really all the exact same. all I'm really doing is kind of expanding by another dimension and generalizing m to f prime of x, or f sub x and f sub y, the partials. And if you can kind of get that, then it makes this a whole lot easier to kind of understand and remember, and you don't have to memorize it as much as just understand it. You can generate it on your own. But just to run through an example to kind of see how this works. So let's see, the one I have. Let z equal 25 minus x squared minus y squared. And I want to find the equation of the tangent line at the point 1, 2. And if I plug in x equal to 1 and y equal to 2, 1 squared is 1, 2 squared is 4. That's 25 minus 1 minus 4, which is 20. So that would be the point in R3. Now I want to find the equation of the tangent plane. I know I'm going to need my partials, my derivatives. So right off, f sub x, the partial with respect to x is negative 2x. The partial with respect to y is negative 2y. And I'm going to need the partials at the point. So f sub x, x is equal to 1, so that's negative 2. F sub y, y is equal to 2, so that's negative 4. So now I have that. Now I have my equation right here. So let's see. Z is equal to f sub x at the point, which is negative 2, times x minus the x value, which is 1, plus f sub y. F sub y is negative 4. Y minus the y value, which is 2. And I left off my x sub 0, y sub 0. I'll just put it at the end, plus 20. I was doing it in the x, y, z version. But whatever. Now I have my equation right there. And if I wanted, a lot of times we did in class, simplify this, I get negative 2x plus 2, negative 4y plus 8 plus 20. So z is negative 2x minus 4y, 2 and 8 is 10 plus 20 is 30. And there's my equation of my tangent plane. If I wanted to get an actual formula for the normal vector, I could just plug it in here. I would point out the partials here are negative. The equation, the vector actually has a negative in it, so then those would cancel out, so don't get confused. But again, from, say, a problem-solving perspective, just like finding the tangent line in Calc 1, find the equation of the tangent plane. Okay, there's my equation, which I know, it's the equation of a plane. Oh, but now where does my normal vector come from? It comes from the partial derivatives. Find those and plug in, and then it's just a direct substitution thing, so it doesn't take a lot of incredibly complex, confusing thinking. I'm looking for a plane, I have my equation, and then I just fill in the details. We are going to expand on this a little bit and use it more in class, but for this video, I just wanted to kind of give a rough overview of what the equation is and how to find it for a given example. And now I get to end this and make another video.